In this lecture, we'll talk about another interesting topic, learning through experimentation and the multi-armed bandit problem. Remember that in the previous lecture, we talked about web advertising, and we already discussed how to match advertisers to queries in real time. But we didn't really discuss how to estimate the CTR or the click-through rate. And we didn't also discuss how to handle the so-called exploration-exploitation problem. And remember, even several lectures ago, we talked about how to build recommendation engines or recommender systems, but we didn't really discuss how to actually handle the cold start problem, and specifically when a new item or cold start item appears, do we choose to recommend this new item to the users, or do we choose to only keep recommending the old items just to be safe? So if you think about it, what do CTR and the cold start problem have in common? The answer is that with every ad we show, or with every product or item we recommend, we will gather more information, more data about the ad or the products. So the theme of this lecture is learning through experimentation, where this experimentation means we recommend possibly a new product to users, or we show new ads to the users. For example, in web advertising, Google's goal would be to maximize the revenue, right? And how does Google make profit? Google makes profit using a pay-by-click model. So basically, that strategy would be naturally go with the expected revenue. Just calculate the expected revenue of showing each ad, and we'll just go ahead and show the ads with the largest expected revenue to the user. But specifically, how do you compute this expected revenue, right? And we already discussed this in the previous lecture. We say that this expected revenue can be computed using the CTR times the bid amount. And here the CTR is the probability that the user will click on this ad A given a query queue, right? And so this probability that a advertisement gets clicked, and the bid amount is the amount of money Google will get if this ad actually got clicked, right? So this is the bid amount, the amount of money that Google bid. And if you multiply them till you get the expected revenue for this ad corresponding to this query. The problem is we do not really know the click-through rate for a specific ad, so we need to gather information. Therefore, we need to do experiments to estimate this click-through rate, and we hope that as we gather more and more data, our estimate of this click-through rate will get more and more accurate. And other applications besides web advertisement include clinical trial, where you will need to choose between keeping the current treatment or exploring new treatment. So if you keep the current treatment, this is safe, but it may not be the best treatment, right? But if you decide to explore new treatment, it can be risky, but it can also be more effective than the current treatment. Another application is adaptive routing, where you need to choose between keeping the current route. So you route the message, you route the package using the current route, or you can choose to investigate new routes. If you choose to keep the current route, it's okay, but it might be time consuming because you can potentially do better, right? And if you, on the other hand, if you decide to investigate new routes, this may or may not be faster, right? If it turns out the new route is actually still worse, than the current round, then you actually lose something. And another application will be asset pricing. So basically, when you want to price some kind of asset, so you need to choose between keeping the current price or exploring a new price. If you choose to keep the current price, it can make expectable money. But if you choose to explore a new price, it may even make more money for you, but it may not. Right? It might even make less money for you. Then another application, of course, is let's talk about AlphaGo. Because AlphaGo may need to choose between using the current estimated best move and exploring an uncertain move for potentially better estimations, right? Then the approach that we're gonna use to tackle this kind of problem, and the formal problem we're gonna talk about in this lecture, it's called Bandit. The name actually comes from imagining a gambler or a bandit playing at a row of slot machines, and this bandit is trying to decide which slot machine he or she can pull such that she can maximize the money she can make. And in here, each slot machine represents one choice, right? And usually in a bandit term, we usually call each slot machine an arm, and this is why we usually call it a multi-arm bandit. Now, more formally, in a k-arm bandit setting, where we have k arms, then each arm A will win with a fixed but unknown probability mu A. So if this arm wins, then we will get a reward of 1. And similarly, this arm can also lose, and it will lose with a fixed probability of 1 minus mu A. So if it turns out you pull this arm and you lose, then you're gonna get a reward of 0. And we also assume that all draws, so basically all pulls, will be independent, given mu1, mu2, all the way to mu k. So the question is, how do we pull these arms to maximize our total reward? And of course, you might wonder, how do we exactly map this k-arm bandit problem to our previous setting on the web advertising? You can actually think of each query in the web advertising as a bandit, and you can think of each ad as an arm. So whenever you pull an arm, that's actually equivalent to showing an ad to some user, right? And if let's say that if a specific arm wins, then that corresponds to some user actually click this specific ad. And here we would want to estimate the arm's probability of winning. So basically we want to estimate mu A here, and that corresponds to the ads, the click-through rate. So the CTR of a specific ad, mu A. And every time we pull an arm, it's like we're doing an experiment, right? And this is also why we call it learning through experimentation. Now, the formal setting of a stochastic k-arm bandit problem is that we have a set of k choices. So these are the k arms that we talked about. And each choice, so each arm is associated with an unknown probability distribution, PA. Right? And it has support between 0 and 1. So you can think of this, for example, as a Bernoulli distribution, right? And whenever you pull an arm, it's like you're drawing a sample from a Bernoulli distribution. So either you're gonna win or you're gonna lose. And if you win, then you're gonna get a reward of 1. And if you lose, then you'll get a reward of 0. And then we will play this game for T rounds, sorry. And in each round, T will first pick some arm let's call this j, and we're gonna attempt some random sample xt from the distribution corresponding to this pj. So remember, this can be, for example, a Bernoulli distribution, and drawing the sample is like you're flipping the coin, right? And note that this reward is actually independent of all previous reward or all previous draws or pulls of the arms. Now our goal is to maximize the total reward. So total reward is just the summation of all the xt, where t index is the rounds. We add up all the rounds of xt, then we get the total reward and want to maximize it. But one tricky thing is that we actually don't know the mu a. Remember, mu a is the expected reward for a specific arm a here. Of course, if we already know mu a, it would be much simpler for us to pick to decide which arm to pick, right? But since we do not know mu a, things would be trickier. But the hope is that every time we pull some arm a, we get to learn a bit more about this mu a, and we intend to use this kind of information to improve our decision. Now, more concretely, let's look at this example on online optimization. Right? You can see that in this case, in the first round, the algorithm will pick the second arm, A2, and it will flip a coin, and it turns out you lose, and it will get a reward of 0. And in the second round, the algorithm take the case arm and will flip a coin. It turns out that you lose again, and then you get a reward of 0 again. And the third round, you have better luck. The algorithm pick the second arm, and it turns out you get a reward of 1 because you flip a coin. It happens to be saying that you win. So etc. etc. And you can see that as the experiment goes on, you actually have more and more information, right, about each arm. So like in the online algorithms, we have to make a choice each time, and the choice is actually irrevocable. Let's say that you already made a decision what arm to pull in the 4th round, and if you're in the next round, you can never go back to the previous round to change the decision. This is what we mean by irrevocable. And then another thing is that we only receive information about the chosen action. So you can see that in the first round, we only choose the second arm, right? So we only get the information about the second arm. We don't know anything. We don't know what would have happened if we chose all the other rounds. And to solve this bandit problem, we usually want to learn a policy. And here a policy is like a strategy or a rule in each iteration that tells us which arm to pull. And hopefully this policy will depend on the history of rewards, right? Because basically we want to use the reward history to tell us the mu a when we try to utilize our estimate of mu a to develop a better policy. So one key question is how to quantify the performance of the algorithm, right? And the answer is regret. So what is regret exactly? How do we define this kind of regret that we mentioned? Let's say that mu a is the mean of the distribution PA, and that the payoff or the reward of the best arm, we denote it as mu star. It would just be the maximization over all the arms expectation, right? So it's like you're picking the mu a with the largest one, expected reward. Then let's say that I1, I2, all the way to IT is the sequence of arms that you pull. Then the instantaneous regret at time t will be mu star minus mu 80. Remember that this 80 is the arm that you pull at time A, right? So this is the regret that you have at time t. This is quite intuitive. And the total regret would be just the summation of all the instantaneous regret over all the time steps. So you just sum up all the LT where t indexes the time step. Now the typical goal of solving a multi-armed bandit problem is to learn a policy, or more specifically an arm allocation strategy that guarantees the following. We want that this quantity of RT over T goes to 0 as the capital T goes to infinity. So basically, we want the amortized or the average regret to go to 0 as this experiment goes on forever. So if we already knew the payoff, let's say we already knew all the mu a for different arm, then things would be very easy. You know, which one would we pull? Obviously, we would just choose the arm with the largest mu a, and we'll just keep pulling the arm, right? And that will give us a 0 regret. And this is the best topology. But the problem is, what if we only in the reality, we actually don't know the mu a, right? So this would be more complicated. And on the other hand, let's say that we only cares about estimating the payoffs, mu a, and we do not really care too much about maximizing the total reward or minimizing the total regret. So what should we do? The best strategy for this is that we will pick each k arms equally often. So basically, for each arm, we will pick this arm for t over k times, and then using this way, we can just estimate mu a, which is the expected reward for arm a, by taking the average, right? We take all these t over k rewards, and we take the average, and this would be the average reward or the expected reward for arm k. And it's easy to see that if you do this, then the total and this total reward would just be t over k times the summation of mu star minus mu a. So if you divide this by t, we can see that it's actually 1 over k times the summation, right? So this is actually a constant, and it doesn't really approach 0 as t goes to infinity, right? And this is not what we want if we want to minimize the expected regret of a multi-arm banding algorithm. And in the next part, we will talk about what algorithm we can develop to really guarantee that we can let this quantity approach 0 as t approach infinity.